Oh yeah, okay, we're on. Right. So question 2. The same gang now living together in their house, all happy with their rooms. They've decided that they'll do the cooking one day of the week. And on Saturdays they'll have a takeaway meal. They each give a score from 1 to 10 to different days of the week. The higher the score, the more the student would like to cook on that day. The results are shown below. This is great, this isn't it? Because it's kind of preparing you for university life, this question. It's really kind of thinking about the wider picture. Isn't that good? Explain how to modify the table so the Hungarian algorithm can be used to find a matching for which the total score is maximised. Okay, well this is just one of those standard things about the Hungarian algorithm. We know this, don't we? The Hungarian algorithm maximises. It finds the what does it do? It finds the, which one does it do? It finds the least cost. That's right, isn't it? It finds the least cost allocation. I haven't got the question here, that's why I'm going over a little bit. So these are, we're looking for these to be the highest cost, but the Hungarian algorithm minimises it. So what we have to do, there's a standard method, isn't there, that you subtract every value in the table from a number. Now, strictly speaking, it doesn't matter what number you subtract it from, as long as that number is bigger or at least equal to the biggest number in the table. So that's all we need to say. We're going to subtract every entry from, well, I think the standard thing to do is to subtract it from the largest value in the table. So in this case, that was 10. So subtract every entry from 10, and that would give it. You don't have to do it, subtract it from 10. If you do a bigger number, the next thing that you do, which is reducing rows and columns, will kind of sort that out anyway. But it just needs to be from a number that is at least as big as any number. There is an equivalent way. I think one person wrote an equivalent method for this, which is to make everything negative and then add a number to it. Is that right? That would do the same thing, wouldn't it? I think somebody wrote that. Did somebody write that? Right. So part 2. Show that the modified table and then modifying the table, then reducing rows first and columns second gives the reduced cost matrix below. So as we said, it doesn't matter what number you're subtracting everything from. Once you reduce the rows and columns, you get to the same point. So let's come up with our new matrix. If we're subtracting all of the numbers from 10, remember this is the table here. So we're going to do 10, take away all of those values, and you get, I haven't got this written down, so we're going to 10 take 10 is 0, 10 take 6 is 4, 0, 2, 5. Tell me if I get any of these wrong. 10 take 6, 4, 8, 0. Live subtracting going on here. 0, 1. 10 take 8 is 2. 10 take 2 is 8. Oh, that was confusing. I nearly put 2 again. 10 take 10 is 0. To those who've done this, do you agree with these numbers?
Yeah, that's all.
Have we got that right? Does anybody agree with that? Right. So that is the first thing you have to do. We have to get the Hungarian algorithm ready matrix, which is now going to do the least cost allocation. Then it says reducing rows first. So we need to reduce the rows first. So let's reduce the rows. Reduce rows. That is subtracting the largest number in each row. Oh no, what we're doing here, reducing rows is we're taking away the smallest number in each row. That's right. So if we take away 0, that doesn't do an awful lot. And we're taking away 0 from that one. 0 from the next one. This is proving to be not the most exciting process. Taking away 1 from all of that row, because that's the smallest number. Take away 1 from all in that row. and take away 0 from 4 in the bottom, because 0 was the smallest number there. So that's the reduced rows matrix. I'm going to switch to page width view now and do reducing columns. I'll fit this on the page right. So then again, taking away the smallest number in each column, 0. 1 from that one, 3, 7, 0, 4, 0, 5. We're taking away 0 from this one. Taking away 1 from this column. 2. And 0 from the last column. There we go. So that is our reduced matrix. And is that the one that they have in the answer book? It is. It's exactly the same. And we got that check that we got the right one. So we got 3 marks for doing that little bit of work. Complete the application of the Hungarian algorithm, stating how each table was formed. Use your final matrix to decide on which day Fred cooks. So, the first thing we do with the Hungarian algorithm, it's kind of slightly mixed up at this point, isn't it? Did they merge 2 and 3 together in the book? Yeah, they moved to a new space. So you could either draw that out again, or I think you were all right to do your starting of your Hungarian algorithm. Yeah, in the previous bit where you cross out, because remember the algorithm starts with you crossing out all of the zeros. Now the important thing here is we want to do this in the least possible number of rows, least possible number of lines that we can do it. That's what we're looking for. If the least possible number of lines is 6, then we've got the optimum solution. So as we start putting lines across this, we'll do it with that. You want to try and get as few as possible lines. So let's see if we can knock out as many zeros as we can. That one looks like that would knock out a load of zeros. That would knock out a load of zeros. How close are we to being there? We've done it, haven't we? That has got all of the zeros, and that was only 4 lines. There are 6 rows and columns in this, so we've done pretty well with that. The smallest uncovered element is that 1 that's there. So we're going to augment this matrix with 1. And make a little note to ourselves that E equals 1. And what that means is that any uncovered element is going to have 1 taken away from it. Any element covered once is going to stay as it is. Any element covered twice is going to have 1 added to it. So this becomes 0, 2, 0, 0, 2, 4. And then we have 4, 6, 0, 7, 3, 3. That's covered twice, so that becomes a 1, 0, that becomes a 3, 5, 6, 0, 0, 3, 0, 2, 1, 0, 1, 0, 1, 0, 0, 1, binary row, 7, 4, 0, 5, 6, 5. That's what it looks like after the first stage of augmenting. Now we have to do the lines thing again. We have to do it in the minimum number of possible lines. Right. So again, the trick is to try. We're trying to do it in as few lines as possible. So let's try and get as many crossed out as we can. We cross out 3 that way. What else does it look like? That one looks like that knocks out a few lines. What have we got left? We've got 2 by going that way, and 2 by going that way. 1, 2, 3, 4, 5. We've got all the zeros with 5 lines, so we've still got a non-optimum solution. So we're going to augment this again. Now it looks to me like E is 3 this time. 3 is the smallest number that isn't covered. So we're going to get quite a big amount of progress at this point. Let's throw those numbers at it, and we're going to get 0, 2, 1. 0, 2, 4. We're taking away, it's not 1, is it? It's 3, sorry, because we're adding 3 is the number that we're augmenting with. 1, 3, 0, 4, 0, 0. 1, 0, 6, 5, 6, 0, 0, 3, 3, 2, 1, 0, 1, 0, 4, 0, 0, 1, and then what's that? 4, 1, 0, 2, 3, 2. Right. We've got to keep going. We've got to keep testing whether we've got the optimum solution. So we're back to our lines that are going on over this. What can we do? We've got one line for knock out that lot, one line that lot, that's 2 lines. I've got 2 zeros, so that's 3 lines. I've got 2 zeros, that's 4 lines. Oh, hang on. If I do, I'm struggling, aren't I? What have we got? 5, 6. I haven't got them all done. Is that really 6? 1, 2, 3, 4, 5. Oh, that's 5.
There's another 0.
And there's another 0, 6. So I can't do it in less than 6. There's definitely no way that I can do them all. And in fact, remember what we said about this is that it should be now. Because we couldn't do it.
7 lines.
Have I used 7 lines? That's
Three on the
just a crazy thing to do, to use 7 lines, isn't it? Because of course, if we're using 7 lines, that means that I could have just done that, and that. Can I get rid of that line? Oh no, I've got lines all over the place. Well, this is slick, isn't it? There we go. There we are. Oh, 6 lines. Improved upon my 7. What we should be able to do now is go through this and mark off 1 in each row and column that is our final solution. Because it should be able to do that. Now look, bottom row there we have only 1 0, so we're going to have to use that 0. Any other time when we've only got 1 0 occurring. Is there going to be 2 another one where we've got 1 0? So we've got a few different solutions here for this one. Well, I mean, kind of the solutions start to jump out a little bit once we start doing that. We could, if we take that 0 there, for example, and let's have that 0, that 0, that 0. Has that done it? I've only set on 5 zeros. There we go. There's the 6th one. That's 1 in each row and 1 in each column. So that is a solution. Is that the only solution? Looks like it might be actually, doesn't it? Because we can't switch things around too much.
No, it's not. It doesn't.
I think maybe it is. Anyway, that's the one that we've come up with, and we need to refer back to what it actually meant initially. So these were days from Sunday through to Friday. These were the people. So we've got, what have we got from this? Alice on Sunday. Beth is Sunday, Monday, Tuesday, Wednesday, Thursday. Corey was Monday. Drew, whose trumpet was on Friday. E was Edmund, I'm going to call him Ed, and he was Sunday, Monday, Tuesday, Wednesday. And Fred was Tuesday. So, and so that was our answer that we came up with. And it said, use your thing to decide which day Fred cooks, so there he is. Fred cooks on Tuesday. Suppose that Alice cooks on Sunday. Oh, I see, there were a number of different answers, and I just happened to pick the one where Alice did cook on Sunday. Sorry. Write a list showing on which day each student cooks according to the matching which the total score is maximised. So that is the one in which Alice does something. I happened to stumble upon that straight away. But there we go, Fred on Tuesday. Because that was the one that there was no choice. So there were other matchings available here, weren't there? It's just that's the one where Alex is doing that. There we go. I mean, you take like you on fair enough. 11 marks. And again, it's one of those questions where you needed to kind of get the first bits right, but they did at least give you a point partway through, because they gave you this matrix here that we were doing our reduction on. So even if you'd messed up the first bit, you had a second way into the question for the big 5 marks of complete application of the Hungarian algorithm, which is the way through that. There we go. Thanks, Jordan.